Today, I want to start by asking you to picture a tropical vacation.
Oh, nice.
Yeah, you know the image. You've got the white sand, the turquoise water.
A palm tree leaning just perfectly over the water.
Exactly. And right there in the sand, you've got a coconut.
It is the ultimate symbol of relaxation, I think, really.
It totally is. But today, we are actually going to ruin that image for you.
Or maybe upgrade it.
Fair point. Yeah, upgrade it. Because we are completely ignoring the fruit. We are ignoring the refreshing coconut water.
Right.
We are looking entirely at the trash, the shell, that hairy, hard, kind of dirty part that usually just gets thrown in a huge heap to rot behind the resort.
Which is a classic case of one person's waste being another person's treasure.
Yeah.
Or in this case, another industry's literal gold standard.
That is the perfect way to frame it. Our mission for this deep dive is to look at a process that takes those mounds of discarded coconut shells, this agricultural waste found on beaches all over the tropics, and transforms them into a pharmaceutical-grade material.
A material is worth hundreds, sometimes thousands of dollars per ton.
Exactly. We're talking about activated carbon. And I want to be super clear here, based on the sources we've pulled, this isn't some backyard bonfire operation.
Oh, far from it. If you walked into one of these manufacturing facilities, you would never think, recycling center.
No.
You would think, wow, this is a precision engineering marvel. It is a total sensory overload. You have temperatures hitting 1800 degrees Fahrenheit.
Which is why
You have the deafening roar of these massive hammer mills. You have steel cylinders the size of buildings just rotating day and night.
And the goal of all this violence and heat, which is honestly the most fascinating part to me, is that essentially we are manufacturing nothing.
Nothing. That is a great way to put it.
Right.
Yeah, we are trying to understand how engineers take a solid object, this rock-hard coconut shell, and drill billions of microscopic holes into it.
Yeah.
We're engineering empty space. We're engineering pores into carbon to create literally one of the most powerful filtration materials known to science.
It's just incredible. So let's unpack this. We have a ton of ground to cover, all the way from the messy receiving yard to this high-tech quality control lab.
Let's do it.
Let's begin at the raw material reception stage. Set the scene for us.
Okay, so picture the receiving yard. It is definitely not glamorous.
I imagine not.
You have trucks arriving constantly dumping just massive loads of coconut shells.
1,000 degrees.
Yeah. And the setup is a countercurrent flow. The solid char flows down by gravity while superheated steam is blasted upwards from the bottom.
I really love the analogy from the source material about what the steam is actually doing here. It's acting like a molecular drill.
That is probably the most accurate way to visualize it. The actual chemical reaction happening is carbon plus water yields carbon monoxide and hydrogen gas.
Okay.
But physically, that superheated steam is literally eating away individual carbon atoms from the solid char. It is excavating an intricate internal structure.
It's drilling holes.
It's drilling billions of microscopic holes.
And the result of that drilling is mind-blowing. The stat that really stuck with me, 1 gram of this activated material, just 1 single gram,
Yeah,
has a surface area of over 1,000 square meters.
it's incredible.
That is roughly a fifth of a football field, folded up into a teaspoon of black powder.
It completely defies logic when you first hear it.
Huh.
But that is the sheer power
Yeah.
of a highly engineered pore structure. But the real engineering challenge here isn't just making pores, it's control. It is an incredibly delicate balancing act.
Oh, so?
Well, if you overactivate it, say you leave it in the steam bath just a few minutes too long, the carbon structure gets entirely eaten away. It turns to useless dust. It just disintegrates.
Oh, wow.
But if you underactivate it, the internal pores don't fully develop and it won't filter anything. It's just a rock.
So they really have to hit that exact sweet spot every single time.
Every time. And once it finally drops out of the bottom of that furnace, it is highly reactive again because of all that fresh open surface area.
Right.
So it has to be stabilized immediately. Usually they use a water quench for this, which actually has the added benefit of flushing out any loose dust from all those newly created pores.
Okay, so now at this stage, we finally have activated carbon. We did it.
We did it.
But it's a big mix of sizes, right? Some of it is chunks, some of it is fine dust. We need to organize it.
We do. This brings us to the refining, screening, and size classification stage. They use these massive vibrating wire mesh decks, multiple layers of them, to separate the product by size.
And the sources talk a lot about PAC and GAC. What's the difference there?
It's an important distinction based on how you want to use the filter. PAC stands for powdered activated carbon,
Powdered.
right? It's a really fine stuff. And it works incredibly fast because the particles are so small. Contaminants hit the surface area almost instantly.
So where would you use that?
You'd use PAC for a rapid chemical spill response, or maybe municipal batch water treatments where you just dump it in and stir.
Okay, and GAC?
GAC is granular activated carbon. These are the larger, roughly sand-sized grains.
Like what's in my water pitcher at home?
Exactly. This is what you want for any system where liquid or air needs to actively flow steadily through a packed bed of carbon without getting clogged up.
But for some customers, I read that just being clean and perfectly sized isn't clean enough. Like if you're a pharmaceutical company, you absolutely cannot have any leftover mineral ash in there.
No, absolutely not. Standard steam activated carbon might still have 3 to 8% mineral ash content left over.
Just from the natural shell.
Right, naturally calcium, magnesium, things from the soil the tree grew in.
Okay.
That is perfectly fine for treating industrial wastewater, but it is not acceptable for purifying liquid medication. So for those high-end clients, we introduced a step called acid washing.
That sounds intense. Acid washing carbon.
It is a very rigorous high-purity process. They take the granular carbon and literally wash it in large vats with hydrochloric or sulfuric acid.
And the acid doesn't melt the carbon?
Nope. The acid completely dissolves the trapped metals and minerals, but it leaves the strong carbon structure totally intact. Then they rinse it repeatedly with highly purified water until the remaining ash content drops well below 1%.
And that tiny percentage drop is the huge difference between industrial grade and pharmaceutical grade.
Exactly. It completely changes the value of the product.
Yeah.
And really, this rigorous testing brings us to the final and perhaps most impressive layer of this modern facility.
The quality control.
The quality control.
Because from what I gather, this isn't just a guy with a clipboard and a magnifying glass anymore. We are talking about serious AI integration.
Oh, a modern activated carbon facility is an incredibly data-driven environment. You have artificial intelligence monitoring the entire thermochemical process in real time.
How does it actually intervene, though?
Well, for example, if the AI sensors see the surface area trending down, maybe the raw coconut shells from that particular delivery were just slightly denser that day,
Yeah.
the system automatically, without human intervention, adjusts the steam injection rate or slows down the residence time in the vertical furnace to compensate.
It's entirely self-correcting.
It is. And then the physical lab confirms what the AI is doing. They use a technique called BET analysis.
BET.
Right. It involves using liquid nitrogen vapor to precisely measure that massive internal surface area we talked about.
And they have some serious visual hardware in there too, right?
They do. This is another tech highlight. They're using scanning electron microscopes. SMs.
Like in a university physics lab.
Exactly. These massive microscopes allow them to see the pore structure at 100,000 times magnification.
Wow.
They can literally inspect the microscopic holes they just drilled with the steam to ensure they are the exact right shape for whatever molecule the client is trying to trap.
That is just wild to think about. We went from a dirty coconut shell getting dumped out of a truck to a manufactured nanostructure that you literally need an electron microscope to verify.
It's a crazy journey.
And you know what the best part is? The overall footprint. The circular economy of the whole plant.
That is definitely the big picture takeaway here. The entire facility is engineered to run largely on its own waste.
Right.
Remember that massive heat generated from the pyrolysis and the horizontal kilns?
Yeah, the 1,000-degree off-gassing.
They capture that waste heat and route it back to run those giant 60-foot rotary dryers we talked about at the beginning.
To dry the raw, wet shells.
Exactly. And the exhaust gases from the vertical furnaces don't just go out a smokestack. They go through thermal oxidizers and industrial scrubbers.
So they are actively cleaning the emissions of the factory that makes the primary cleaning material.
It is a beautifully closed loop. They capture their own heat, filter their own air, and turn waste into gold.
So stepping back from all the heat and the robots, what does this actually mean for us, the listener?
It means that hidden quietly behind the scenes of our daily lives, every time you pour a glass of filtered water from your fridge, every time a massive gold mine operates without contaminating the local river, every time a life-saving pharmaceutical drug is perfectly purified,
Yeah.
there's this massive, extremely hot, deafening, precision-engineered process making it entirely possible.
It really does change how you look at something as simple as a glass of water. Next time you take a sip, you kind of have to think about the 1,800-degree steam bath and the little coconut shell that made it taste so clean.
You really do. And think about
Yeah.
the human engineering involved. We took agricultural waste, something that was literally just going to rot on a tropical beach and release methane,
Yep.
and we turned it into an industrial lifesaver.
I love that. It's a perfect example of the hidden engineering inside everyday objects. But I want to leave you with one final thought, something we didn't explicitly cover but builds on everything we just discussed.
What's that?
If we can engineer these microscopic pores to be so specifically tailored that they grab impurities out of water and medicine, what if we apply that to the air on a global scale?
Direct air capture.
Exactly. Researchers are already looking at highly advanced, modified, activated carbons to selectively trap carbon dioxide right out of the atmosphere. The same technology that purifies your tap water might eventually be the exact mechanism we use to help filter greenhouse gases out of the sky.
Now that is a really powerful thought to end on.
Something to mull over. That's a wrap for this deep dive. Thank you so much for joining us, and as always, stay curious.
See you next time.